Hi, folks. This is a lesson on the angle-angle triangle similarity theorem. This is from Unit 3 on similarity. And by the end of the class, you should be able to say, I can prove two triangles are similar when they have two corresponding congruent angles. The similarity theorem, similarity symbol is a tilde, so it's not congruent. It's not with a tilde over an equal sign. It's just the tilde. The second objective is to reconfigure two similar triangles to have like configurations so that we can set up our proportions and solve problems. Here we have two triangles, ABC and DEF. And the question is, well, they both have a 106 degrees and they have a 31 degree angle. And they're not congruent. They're not the same size. Are they similar? Can you explain? And what if you had two other triangles with different angles? The idea was to make a conjecture about them, and the conjecture would be, I think that two triangles will be similar if they have two corresponding congruent angles. So in reference 3, and on Unit 3, there's a reference chart. You can open it, but you have your own reference table. And you want to make sure that these ideas get into the reference table. If I were to open this document, you can see here scale factor. Scale factor is the factor by which every length of an original figure is multiplied in order to make a scaled copy. That is, the lengths are multiplied, not the areas, the lengths multiplied. A dilation, and this is a definition for dilation. And then we have some other things in here. One of them that we're going to be talking about more today is this angle-angle triangle similarity theorem, which says in two triangles, if two pairs of corresponding angles are congruent, then the angles must be similar. And so I go back to my Desmos. A dilation with center P and a positive scale factor, which we'll call K, takes a point A along the ray PA to another point whose distance is K times farther away from P than A is. So in this activity, we're going to prove the two triangles are similar. If you go to this applet, this GeoGebra applet, here we have two triangles. I'm going to make this angle, I think I'll make it 90. I'm going to show you how this applet works. If I want to make this angle here 90 as well, and I can lock these by clicking on this, doing my lock symbol, and matching up the angles. Now this angle is 56 and this one is 56, so I can lock them as well. And now I have two triangles with two angles that are congruent just by the angle. Is there a set of rigid motion transformations and a dilation, which is not rigid, that will map the one triangle onto the other? To try that, you can click on the triangle, you can drag it. And when you drag it, then we can also rotate it by clicking on it. I want to reflect it across the line that goes through this point and this one. I also want to rotate it around this point. I want to rotate around this point. I want to match it up to this other one. And now I don't quite match up. And then I want to dilate it. To dilate it, I have to have a point of dilation, and I can make it larger. And you can see that there is. In other words, you can always map two similar triangles onto each other by a set of rigid transformations, that is, translate, rotate, and reflect, and a dilation, which is getting larger or getting smaller. And two angles, as shown in this visual proof, is sufficient to prove that. We could have written it out in words, but instead we chose to do it visually with this applet. So you were to demonstrate that the sequence of rigid transformations and a dilation exist that map one triangle onto another, given two angles of the one triangle are congruent to two angles of the second. Although this was done visually, you could have been written down to accomplish the same. This is called the angle-angle triangle similarity theorem. And please make sure that this makes it into your reference table. Now, I've taught math for some time, and there are only 5 different configurations that have ever come in across. I've not come across any others. If you do, that'd be great for you, and you can let me know. But these are the ones, and I've given them names. So I call them the parallel inside, parallel outside, the butterfly, crazy, and the geometric mean. And let me explain to you how these work, so that you can try to get an idea. Here I have, yes, we have corresponding angles that are congruent. And I also have, so I could have marked these other ones to have angle-angle similarity. I also have, by the reflexive property, this angle is congruent to itself for both the large triangle and the small triangle. And I could redraw these triangles. I could draw it like this and like this. And if I draw them with the same configuration, then it makes it really easy to be able to set up a proportion. And that's the whole trick here. If you want to call it a trick, the idea is to redraw these so that they have the same configuration. Here I have alternate interior angles formed by the transversal crossing parallel lines. We also have these two angles are vertical pairs. So I could redraw this. I'll draw the first one the way it is originally. And I'm going to redraw the second one like this. So when I go to label it, I can mark it down here, and then I could set up a proportion. Again, we have vertical angles here. So I could redraw the first one like this, and I could redraw the second one with this, redraw the second with the same configuration. So I've got the angles in the same place. I've relabeled the sides. This one is just crazy. Notice I have 2 angles here that are the same for one pair of angles, but this angle by the reflexive property is the same for both the small and the large triangle. And if I were to redraw this, then I have this, and I have this. Redrawing it only takes a moment, but it will save you a lot of problems when it comes time to solve to setting up the proportion correctly. We know how to solve proportions. The question is, can you write the proportion correctly? This is a right triangle. It's a right angle. It's got a one arc and then 2 arcs. Well, this is a right triangle. It's got 2 arcs, so this other one has to be 1. This is a right triangle. It's got a 1 arc, so this has to be 2. Can you see that there are 3 triangles with the same configuration? Three triangles, and if I mark them with the same configuration, say putting the one tick up here, and now I've got angle-angle similarity for all of them and redrawing them. This is the geometric mean, and it will merit discussion of its own. So the idea is to redraw them so that you can set up a proportion. Large triangle is to small, it's large is to small, A is to B, is C is to D. Here we're to determine whether they are similar, and if they are, to write an explanation. You can copy over my lettering here and then re-letter it, but copy over the symbol of the triangle. The symbol, I know that you have a tilde on your keyboard, so you could actually type this one, but the triangle may not be so easy to copy over. Maybe I'll just copy over the triangle. In this first one, I have a triangle with a H, which is 90. G has 48 degrees. This one doesn't have a 48 degrees marked, but how much is angle L? The 3 angles have to add to 180. So 48 plus something adds to 90. This is going to be the, so I'm going to have 2 similar triangles. They don't necessarily have to be congruent. I'm going to copy over my triangle symbol, and I'll say HGF. That's 90, 48, F. And that's going to be similar, using the tilde on my keyboard, to triangle. The J corresponds to the H, that's 90. The L corresponds to the G, that's 48, and then the K. So you go through and you mark these. After you've done so, you'll notice that B and C are not similar. They do not have 2 angles that are the same. But D does have 2 angles that are congruent, and with 2 angles congruent, you can know that they are similar. What is the problem here? Please think about it and then listen to my spoiler. This is the angle-angle similarity is for triangle similarity. It does not work for quadrilaterals. And you can think about that. If you have a rectangle, it could be a square. 4 angles are congruent, and then you can make it really longer. So it should be relatively intuitive that no 4 angles is not enough to prove that 2 quadrilaterals are the same. Here, this person made a mistake, and your task is to figure out what she did wrong, and or he did wrong. The math over here looks good, except the proportion is not good. Well, this person didn't do what I said to do. First of all, you have an angle here that is congruent. This is congruent to itself. So I will redraw both of these with the 2 hash marks at the top and the 1 here. And I'm going to redraw them so that they look the same. This is the parallel inside version of what we had. This is 4 and this is 6. And we know that the bottom part is x. This side is not 5. 5 plus 4 is 9. So when I set up the proportion, I get 4 is to 6. Short side is to long side, as 9 is to x. And when we cross multiply, we get 4x is equal to 54, and x is equal to 54 fourths. Now, I like improper fractions, but I like them to be simplified. Both have a 2 in common. You have 27 halves. So this would be my answer. If you put it as a decimal, that's okay, but I prefer to see it this way. And the rest of the questions that are in this activity are all about separating the triangles, lining them up with the like configuration, setting up your proportion, and then solving it. And that's all there is to this lesson today. Lots of practice, which you don't finish during class, we would have you do for homework. So please try to do all of these exercises and get experience with doing them. Some of them are a little bit trickier than others. Good luck and success.